Hi everyone, my name is Dennis, I'm with Nvidia, and today I'll be presenting a live video workflow that operates on 8K sources and detects objects and tracks them, and we see how it all performs on GPUs, RDMA-capable NICs, and what improvements can be made in various scenarios. Okay, so when you're capturing a live event, in all cases there are multiple cameras, there's quite a lot of cameras involved, and the more cameras you have, the more complex it is and the more expensive things are. Now, okay, if you have different cameras on opposite ends of a stadium, obviously there's not much you can do about it. You need different vantage points, but oftentimes you have multiple cameras in the same general place, and they're all looking in the same location, and they're really just zooming in onto various objects that they want to track. Now, what would be really nice if instead you could have just one camera and you could use software to crop out the regions of interest and then proceed to track them. And this is exactly where 8K comes in, because normally, I mean, if you do that and you crop it out, your crops are not going to be a particularly high resolution. But if you're initially capturing an 8K, that's when you can crop out something like HD. And I mean, there are cameras that are capable of sending UHD up to 120 FPS live and not just recording the footage. At the same time, on the processing side, there are NICs that can receive those kinds of flows, and they can actually move the data, uncompressed buffers, even directly on the GPU without having to go through system memory, without having to go through the operating system kernel. And GPUs, of course, can process that workload. So the hardware is there. What we would really like to see is for complex software pipelines to be able to efficiently exploit the hardware to make it all happen. So just to go over the workflow, everything starts at the camera. Camera captures a frame. An ML algorithm is used to detect objects of interest, so like players in a sports game. And then we choose whatever region we want to crop. Here in the red, it's a laser pointer here. Yeah, in the red here, you could see the thing is cropped here. And so we crop it, then we encode it, mux it, whatever, send it off. So this talk is actually not so much about the encoding, it's more about processing the uncompressed frame. Decoding it is a part of it, depending on what format it comes in. The encoding part is the least significant here, so this is less about encoding. So this is all happening on either a workstation or a server that has one GPU, that can have at least one GPU and an RDMA NIC. So first step, oh yeah, and we want to containerize this because typically on these servers and even workstation machines, they can have 40 CPUs, sometimes more, and we really don't need all those resources. What we definitely need is we need one GPU to process this kind of pipeline. But we don't even necessarily need a NIC for the entire pipeline. We can actually launch multiple of these using the same NIC. We do need multiple GPUs, which can fit on these machines. So we do want to containerize it. So first step is we capture the stuff, and it's received through our RDMA. Since we're capturing at a paced manner, it comes in packet by packet. Next, we typically either do a color space conversion if we capture raw, or we do a decode for something like JPEG XS. And this is all happening on the GPU since we can get the data directly on the GPU. We run a detection algorithm with CUDA. After that, we run some other operations both with CUDA and CPUs for re-identifying the detected objects frame after frame to recorrelate them. And then we run a crop. That's not really a big deal. We do another color space conversion just to prepare it for encoding, and then we send it off on its way. So just to put the workflow in perspective of a pipeline, first of all, it looks, as time-wise, it looks closer to this, at least for the 8K, 60 case. This is pretty close. One of the steps, the re-identification steps, is actually broken down into two. First one is feature extraction, which is another convolutional neural net. What it takes all the detected objects, it makes a similarity vector for them, and then the re-ID step, it takes these similarity vectors and tries to figure out which corresponds to which in subsequent frames, and furthermore, it's like, yeah, and then there's other filters applied, like Kalman filter. There's a range of things that happens in this spot. So it's also in this step, so it's also significant. Anyways, so First frame, so before we can do anything else, we have to receive the frame. And since it's being captured from a camera and standards, which in this case we use SMPTE 2110, everything arrives in a paced manner. We're not going to be able to do anything until 1 divided by the FPS. So first frame comes in, we start processing it, and immediately the second frame starts coming in right as we're processing the first frame, and so on. So that's the pipeline visualized. And so the input scenarios we're using, so 10-bit YUV422 all around, that's the broadcasting standard. 2 experiments, so one 8K at 60 FPS, the other one we tried 8K at 120 FPS. Codecs, so we used RAW. It should work. I got it to work for 8K 60. I admit I did not get it to work for 8K 120. Even if I did, I probably wouldn't go for it. I mean, it's pretty impractical. If we're going to want to run multiple of these on the same NIC, on the same server, we really don't want to be multiplying 42 gigabits per second n times. So for this, there exists JPEG XS, which is very suitable for this. So it allows the apparent quality to remain the same as RAW, apparent quality, but it's transmitted in the same way as RAW is transmitted, but a whole lot less data. And GPU codecs do exist, so we can decode it directly on the GPU, luckily. Of course, it's not free. It incurs a cost. We still have to decode it. We don't just do a color space conversion. So the way, when I'm going to be talking about latency, the way it's measured here is I don't measure glass-to-glass latency. It's not in the order of seconds. I measure from the moment the first packet arrives of a frame right up to the time that the whole encoded H.264 frame is available. I don't measure muxing, packetization, or anything beyond that, just those things. So here I showed you a visualization of the pipeline. This is what happens on the GPU when this is done. So to walk you through it, so this is the moment a frame is received. Here, in the case of a RAW, it's actually more significant than it usually is. We do a memory-to-memory copy. This is not a zero-copy thing, and for good reason, actually. We then do a color space conversion. Then we run the detection model. You can see there's many steps to it because it is a convolutional neural net with many layers to it. Next, this is what's it called? This is the feature extraction, so getting the similarity vector. Next, this happens on the CPU. This is the re-identification, so this is also significant. And lastly, well, not lastly, it's not shown here, but we do the crop and the color space conversion on the GPU. It's just, this barely takes up any time, so it's somewhere down below in another queue. And finally, we do the encoding. So that's one frame. This looks pretty reasonable. If we're using JPEG XS to decode as opposed to RAW, this looks a little differently, not too much differently. The main differences are actually right here. So here you have 2 things. We parse the bit stream and we decode it as opposed to just doing color space conversion and the copy prior to that. So those are the differences. Okay, better move quickly. So the results we got for 8K60 were pretty good. It keeps up, that's the main thing. It doesn't use much GPU, more on that later. However, when we tried to do 8K 120 with this exact setup, it did not keep up, more on that later. So going back to 8K60, fact is it worked pretty well, but it didn't really make much use of the GPU. So as a result, it'd be interesting to see what we can improve, what we can do on it to improve it in such a way that it uses more GPU, but something gets improved. So one thing we can do is we can actually run the detection on a larger canvas, because currently, even though we're getting 8K and the crop is happening on the 8K, we're actually running the detection model on 4K, just because usually these things are even run on even smaller canvases like 540p. But if you try running that on 540p, you're barely going to get any detections most times, unless you've actually trained your model in such a way. But so we do it on 4K, but why not try doing it on 8K? Now, not every detection CVAI model is going to allow you to do that, but the one we use do DetectNet version 2. So that's obviously going to take more time, but we have the time to, but we have the time to spare. So the other thing is, why not try processing the frame, since we do have to wait for that first frame to arrive and not really do much as we're waiting or do whatever we're doing for the previous frame. Why not start processing it when a certain slice of it arrives? That way we can reduce latency. Other thing is, why not try doing both? So first part is slicing, just to kind of visually explain what I mean. So in the normal case, you're waiting for the frame to arrive, and as you could see on the top right, like nothing is being done as you're waiting. And all of a sudden, there's like a burst of GPU workload that you do, but then as you're waiting for the next frame to arrive, and you're not doing much. And now, if you divide it into 3 slices, then, of course, you have to wait for the first slice. Not much you can do there. But once you receive the first slice, all of a sudden, you can start doing something. Same thing, you receive the second slice, wait for the third, but you've already started to process it. And same goes for the last slice of the previous frame, wait for the next slice, and so on. So, I mean, what this doesn't increase GPU utilization that much. It spreads it out over time, but every single pulse of GPU utilization is actually smaller, so it kind of cancels them both out. But latency does benefit, as we're going to see here. So this is the original case, just on a different setup, so it looks a bit different. This is the original case without slicing now, and this is the latency that we get in this particular frame. Now, when slicing, it looks a little different. So here we have the first slice being processed. Then we have, re-identification. Then we have the frame arrive, the second slice being processed. And so finally then we crop both of them. Actually, we can do it at the same time. We color space converge. And we then go ahead and encode it. So re-ID here actually took a bit longer because we have to converge both the detected objects from both the slices. But in any case, this here, we save a bit on latency. So there is that benefit. Now, the other thing of using a bigger canvas, this is how that looks like. Oh gosh, I only have a minute left. Okay, so we have, everything looks more or less the same. Everything looks the same except for the neural networks, so especially the detection one that you see right over here. Well, this one only takes this much time, this one takes a hell of a lot more time. Reason for that is that it's not just because the frame is larger, but as you can see, it's actually toe-stepping with the feature extraction of the previous frame, and that causes some conflicts to occur. So 2 things going on, and the feature extraction itself is taking longer for mainly that reason, actually. So, and nonetheless, though, we can still tolerate that, and I mean, obviously the latency is increased here, but at least we get the better quality of inferencing and more accurately detecting objects. Now, we can also do both. We can do both those things, and by doing both those things, we can actually decrease latency. So this is a lot more squeeze than it was. I don't think you could squeeze it any further, but at this point you can still get. So one note here is, I probably don't have time to go over this now. I'm actually out of time, but you have to measure latency slightly in a different manner, at least in this visualization when you're dealing with slices. Okay, so the results, so much better when we do inference on a bigger canvas, way better than smaller canvas. Now, GPU utilization didn't increase. Oh, crap. Hold on. Okay, back in the table, GPU utilization didn't increase by much, but nonetheless, the latency went down. So for 8K 120, the case that didn't work, this is not even about latency here. We just simply need it to work. One thing that worked is the following optimization. So we do a sort of form of micro-batching. We process one frame halfway through the pipeline. So we receive it, we decode it, we don't run detection on it quite yet. We sit and wait for the next frame to arrive and go through the first half of the pipeline. And as soon as that's happened, we take both the frames together, we run detection on both of them, feature extraction. That way what we're doing is we're saturating the GPU more. Instead of having to run heterogeneous workloads on it, we actually run the same workload in a very coherent manner. and that makes better use of those heavy, GPU-heavy steps. And that, of course, that takes a penalty, since both these encoded frames, they come into these pairwise bursts. I mean, at one point or another, if you want to play this back properly, you're going to have to buffer it, and you're going to have to add 1 frame of latency somewhere in the future. So that's the penalty, but given that it wouldn't work anyways, I think that's a fair penalty to take. So more stable GPU processing, less toe stepping, and that's really why it works. So this is what 8K 120 looks like. There is a whole lot of things conflicting with a whole lot of other things in this pipeline. And even like between, you can see there's like a big gap between the decoding and the copy. Like copy color space conversion doesn't even take that long. It just takes that long to schedule the workload to the GPU, because all the 8 allocated CPU, all the threads are fighting over the 8 allocated CPU resources. And there's also some contention as well. It gets kind of messy at this point. Okay, and this is feature extraction, re-ID, which takes noticeably longer, and then crop. Crop shouldn't even take that long. It's just the GPU happens to be busy at this time. We encode it, and so then when we batch, things actually look a little better. It's far from perfect. So yeah, here, like if we measure, you know, from one frame or another, it doesn't even make the throughput requirement here, not in any instances. I don't think I've seen, like on average, I think it's like about 10 or so. I don't think I've seen anything that even comes to 8. So in this case, yeah, in this case, we receive the frame, we decode it, we receive, yeah, the first frame, and then we do the same, so we receive the second frame shortly afterwards, and we then, when we run detection, that's run on both frames, and same goes with the feature extraction and re-identification. So that's run in a batch, and so for every 2 frames, these 2 steps are only run once as opposed to running them per frame. So that greatly decreases the likelihood of them coming into conflict with something else or even with themselves oftentimes. Not always, but the probability is less, which as a result makes this work. So this keeps up, which is what we're after. And yeah, so that's it for, yeah, so if we measure like these 2 instances, like on average this keeps up. It doesn't go beyond, like if you have like a leaky buffer, I haven't seen it go beyond 1 frame unless you run into thermal issues. If your workstation server, it's not a problem.
Apologies, Dennis.
Yes.
Sorry.
Yeah, sorry, went way overboard.
Would you like to have concluding words?
Oh, yeah, just the table here. Other than that, no, that was pretty much it. Okay. Thank you.
Thank you very much, and apologies again for the tight technical.